Hello, I'm David. I'm a PhD student at EPFL in Switzerland, and I'm going to present our work from the Laboratory for Data Security, which is about scalable, privacy-preserving distributed learning. In order to obtain accurate and generalizable machine learning models, their training usually requires large and diverse data sets. And in order to obtain large enough data sets, data often need to be shared among multiple entities. And this is where distributed learning comes into place, as multiple entities will collaborate in order to train machine learning models on their joint data. The problem is that when the data are sensitive or personal, they are difficult to share among multiple entities because of data regulations such as GDPR in Europe, because all entities that want to participate in the data sharing need to sign data access agreements among themselves, and because when the data are sensitive, the risks are higher and there can be high repercussions for the entities in case of data leakage. And finally, entities that have similar types of sensitive data often compete among each other and do not want to share the data among each other. For all these reasons, sensitive data are often siloed, and entities simply train machine learning models on their own data, which are less diverse, smaller training data sets, and which results in less accurate machine learning models. In order to solve this issue, multiple solutions have been proposed. There are fully centralized solutions in which all the entities send their raw data to a trusted third party, which will then train the machine learning model on the gathered data set. There are meta-analysis solutions in which entities share partial results or aggregated data in order for the trusted third party to perform the last step of the computation and obtain the model. And there are also fully decentralized solutions that work similarly as meta-analysis solutions. So all the entities share aggregated data in order to perform a computation. Finally, there are privacy-preserving solutions which rely either on differential privacy or on cryptographic mechanism in order to protect the exchange information. In the case of differential privacy, the exchange information are protected by adding some noise to them, so partially obfuscating the intermediate results. And in the case of cryptographic solutions, the exchange information is protected by relying on, for example, secret sharing or encryption. The problem with fully centralized meta-analysis and decentralized solutions is that they share information in clear. This can be raw data or aggregated data, and in both cases, it reveals some information about the original data. In the case of differential privacy-based solution, some bias is introduced on the intermediate results, which also introduce bias on the final result, which can be less accurate. And finally, solutions that rely, for example, on secure multi-party computation often only relies on a limited number of parties, for example, between 2 to 4. They are only efficient in this case, which means that the data have to be outsourced to this limited number of parties, which come back to the problem that we mentioned before about data access agreement, data outsourcing. And so we propose a new solution that we call Spindle, which is based on multi-party homomorphic encryption, which we will describe a little bit later, and in which we want to ensure data and model confidentiality, which means that as long as one entity is honest, the data and the model are never revealed. We want the data providers to be able to keep their data locally, so no data outsourcing. And we want our solution to scale with the number of parties and to not introduce by design bias during the computation. In order to build Spindle, we will rely on the gradient descent, which is widely applicable and can be used in order to train many types of machine learning models, and on multi-party homomorphic encryption in order to protect the exchange information. We will combine these two building blocks in an extended MapReduce abstraction, which we use in order to describe the workflow and to identify which information in the workflow have to be protected in order to ensure data and model confidentiality. Finally, we instantiate our generic system for the training and evaluation of generalized linear models, which includes linear, logistic, and multinomial regressions. And we use this instantiation to compare it with existing solutions and to also assess its performance. So now we will walk through the MapReduce workflow before identifying which information have to be protected and also see how this information will be protected. In the first phase, the prepare, the data providers agree on security and learning parameters and then locally pre-process their data. Then they enter in an iterative process in which they will iteratively perform the MapReduce workflow. In the map phase, all the data providers locally train the model with their own local data before combining the resulting models in the combined phase, such that a global model can be updated in the reduce phase. This result is then sent back to the data providers, which with this information again enters in the map phase, and this process is repeated iteratively. At the end, the trained model can be used in order to perform prediction. So a querier can enter the system with new data and ask for prediction on this data to one of the data providers. Now we will see which information and how this information can be protected during the whole process. So each data provider will have a public key and a secret key, and then they will combine their public keys in a collective public key, which is a combination of all data providers' keys. This is performed in the prepare phase. And then this collective key is used in order to encrypt all the informations that is exchanged among the parties. We can see here that the informations that are exchanged are the model at each step of the process. And in the prediction, the trained model, which can remain encrypted, is also used on encrypted data. So these data are, again, not revealed in the system. In order to implement this protection mechanism, we rely on multi-party homomorphic encryption. As I said before, this multi-party scheme relies on a public collective key in order to encrypt the data, and each ciphertext contains a vector of values. On this vector of values, the data providers can independently compute, so perform addition, multiplication, or rotations without having to communicate with the other data providers. However, they need to collaborate in order to decrypt data, which means that all data providers have to agree in order to decrypt any information. And we also rely on the multi-party nature of the encryption scheme that we are using in order to replace costly cryptographic operations, such as the bootstrapping or the refresh of a ciphertext in homomorphic encryption by lightweight interactive protocols that are executed among the data providers. Finally, in Spindle, we rely on an adaptation to the CKKS crypto scheme of the multi-party solution proposed by a team in our laboratory, so the Laboratory for Data Security at EPFL, which will be presented by Christian Mouchet in this conference on Thursday in session 7B. Then, now that we have some encrypted information in the workflow, we have to see how to still perform the workflow in an efficient way. So how to compute on the encrypted data in multiple iterations without adding too much overhead. And in order to do this, the challenge is to perform the operations in the gradient descent in an efficient way. The main operations that we have to perform are in the map phase. At each iteration, each data provider has to multiply a vector, which is encrypted, which is the model, with local clear text data, a matrix of local clear text data. The result of this operation has to be activated through the activation function, which is the sigmoid in the logistic regression, for example. And then the result is again multiplied with a clear text matrix of data. So we have two multiplication between an encrypted vector and a clear text matrix to perform. Spindle chooses the best multiplication approach by taking the input dimension, so the size of the vector and the size of the matrix, in order to choose the best approach. And in both proposed approaches, we minimize the amount of computation that have to be performed on the encrypted data and do most of the transformation on the clear text matrix. We propose two approaches, which are the row-based, in which the matrix is packed in one vector before doing one multiplication, and a diagonal approach in which the clear text matrix is rotated such that we obtain the diagonals of the matrix before doing the multiplication with the vector. Finally, the activation function, which is a non-polynomial function, has to be evaluated on an encrypted vector with homomorphic encryption, and is therefore to be approximated by a least square approximation, which gives accurate results. Another challenge is the parametrization of the system, as the cryptographic parameters are tightly linked with the learning parameters and with the approximation parameters that we have to use in order to approximate the activation function. In the paper, we propose a more detailed directed graph model, which helps the user to choose the parameters by starting from the input dimensions to the all the other parameters. In this slide, we see that Spindle achieves a similar accuracy as non-secure distributed solution. In fact, in this graph, we can see that the results in blue are the results of a centralized approach. In red, it's the result of, or the accuracy achieved by one data provider out of 10, training the same model, but only on its subset of the data. In yellow, it's the result achieved by a non-secure distributed solution. And in green, it's Spindle's accuracy. We can see that Spindle achieves almost the same accuracy as the centralized approach and achieves the same accuracy as a distributed not secure solution, which means that the slight decrease in accuracy that Spindle gets with respect to a centralized solution comes from the distribution of the data and not on the not from the privacy preserving mechanism in Spindle. Now, in terms of scalability, we can see that when the number of features of the model to train increases, Spindle runtimes remain constant up to a certain point. This is because the operations are efficiently parallelized in the data providers and among the data providers. And after a certain point, the runtime starts to increase logarithmically with the number of features. Now, in terms of scalability with other dimensions, we can see that the runtime of Spindle remains constant when more data providers are added to the system, and these data providers bring also more data in the training. In this case, since the workload is efficiently distributed among the data providers, the runtime remains constant. Again, in this graph in the middle, we can see that since the workload is efficiently distributed, if we have more data providers for a constant amount of data, then the runtime decreases as there are more data providers splitting the work among themselves. And finally, on the right of the slide, we can see that when data providers have more data locally, then the runtime of Spindle increases linearly with the size of the local data sets of the data providers. To conclude, we propose a generic framework which enables the privacy-preserving execution of a cooperative gradient descent among a large number of data providers. The cooperative gradient descent is pretty generic, which means that it can be used in order to train many types of machine learning models. And we show how to perform it while protecting both the model and the data confidentiality during the whole training process, but also during the evaluation process, meaning that the model that is securely trained and never revealed can then be used in order to perform predictions without revealing the model. The data stays in the data provider's premises, which means that the data providers do not need to outsource their data to other parties in order to participate in the computation. Spindle achieves almost the same accuracy as centralized non-secure approaches and achieves the same accuracy as non-secure distributed solutions, and also shows the same trade-off as non-secure distributed solutions, or even as non-secure centralized solutions, in the sense that accuracy is only traded off with performance. So if we do less iterations, then we obtain a less accurate model. But accuracy is not traded off with privacy, which means that in contrary to, for example, differential privacy-based solution, which means that we always achieve the same level of privacy without any effect on the accuracy. And finally, we have shown in the previous slides that our system efficiently scales with the number of data providers, the size of the data set, and the number of features in the data set. In our future work that we already started, we show how to apply a similar approach to train more complex machine learning models, such as neural network, and how this approach can also be used in the biomedical domain, in which data are very sensitive and in which the computation task can be executed on very large dimensions, such as a GWAS. And we show that even in this case, our approach is still efficient. Thank you, and see you online for the questions.